Welcome to the deep dive. We take interesting sources, dig through them, and pull out the really key insights for you.
Yeah, kind of like the Cliff Notes for complex topics.
Exactly. And today we're pointing our telescope, metaphorically speaking, at our own backyard, the Milky Way.
Our galactic home.
Right. And we're using this one specific document, Perryman Gaia 006.pdf, as our main guide for this exploration.
It's a great starting point. It really lays out the massive ambition behind the Gaia space mission.
Okay, so let's get into that. Gaia wasn't just counting stars, was it? The source makes it sound much grander.
Oh, much grander. The goal was like mapping 1 billion or more stars, and not just where they are, but with incredible precision.
Precision in position, motion, what else?
And their characteristics, too. Fundamental stuff, where they sit on the Hertzsprung-Russell diagram, basically. Their stage of life and temperature.
Okay.
Their metallicity, what they're made of besides hydrogen and helium, and even how much dust is blocking their light, the reddening effect.
So it's about really knowing the stars, not just cataloging pinpoints of light.
Exactly. The source really hammers this home. The core goal was understanding the Milky Way itself, its dynamics, how it all moves and interacts, its structure.
With it formed, its history.
Yeah, all of that. And the key tool was creating this huge, well-defined catalog of star positions and, crucially, their 3D velocities, how they're actually moving through space.
Which is a massive step up from what came before, right? I think the document mentions Hipparcos.
It does, yeah. Hipparcos was revolutionary, providing that kind of 3D motion data.
Hmm.
But mostly just for stars relatively close to us in our solar neighborhood.
Ah, okay. So Gaia's ambition was galactic scale.
Totally. Taking that detailed neighborhood map and trying to extend it across a huge chunk of the entire Milky Way. It's like going from mapping your city to mapping the whole continent.
Wow. Okay, that puts it into perspective. So to map the continent, you need to know the main regions. What are the big structural parts of the Milky Way mentioned in the source?
Right. The source breaks it down nicely. First, you've got the most familiar bit, the flat disk.
Spiral arms, lots of stars.
Hundreds of billions of stars, yeah.
Yeah.
All different ages. Plus loads of interstellar gas, hydrogen mostly, and dust. And that's where we live. Our sun is in the disk.
It's out 8.5 kiloparsecs out from the center, it says?
Roughly, yeah. Around 27,000 light years, give or take.
Okay, so the disk. What's next, moving inwards?
Towards the center, you hit the bulge. It's less flat than the disk, more like a central swelling.
Right.
It's packed with mostly older stars, and there's evidence it might have this sort of bar shape running through it.
A bar of stars.
Yeah, a dense, elongated structure. And smack bang in the middle of that bulge.
Don't tell me. The supermassive black hole.
You got it. Sagittarius A, about 3 million times the mass of our sun.
Still mind-boggling every time I hear it. Okay, disk, bulge.
What about further out?
Surrounding all that is the halo. It's much more spread out, kind of spherical.
And what's in the halo? Mostly really old stars, about 1 billion of them. And they're metal poor, meaning they formed very early on before lots of heavier elements got cooked up in later star generations.
Like galactic fossils.
Kind of, yeah. It tells about the early days. The halo also has about 140 globular clusters, these incredibly dense balls of ancient stars, and even a few small satellite galaxies orbiting the Milky Way.
Wow. And then there's the invisible part.
Ah, yes. The source mentions the dark matter halo. Enveloping everything we can see, disk, bulge, stellar halo, is this, well, massive halo of dark matter.
The stuff we can't see but know is there because of gravity?
Precisely. We don't know what it is or exactly how it's distributed, but it provides most of the galaxy's mass and gravitational scaffolding. It holds the whole thing together.
Fascinating. And the source stresses that this whole structure isn't static, right? It's always changing.
Absolutely. It's a dynamic system. Gravity is pulling everything around. Stars are being born, dying.
And the galaxy itself changes shape.
Well, yeah, internal things like the bar structure or warps in the disk can shift things around. And then there are big events, like mergers.
Mergers, like galaxies colliding.
Exactly. If a smaller dwarf galaxy gets pulled in and absorbed by the Milky Way, that event stirs everything up. It changes the orbits and distribution of stars significantly, like stirring cream into coffee, as the source puts it.
Okay, so to understand this complex, evolving system, what do astronomers really need to measure?
The source is clear on this. You need accurate distances and space motions. Velocities in 3D.
For lots of stars.
For huge numbers, yes. And crucially, for a really diverse sample. You need stars of different masses, different ages, different metallicities, that chemical composition marker, and at different points in their lives.
So you get the full picture, not just one type of star or one region.
Exactly. You need a representative sample to understand the whole population.
Which brings us right back to Gaia's strength, the numbers, the accuracy.
Precisely. The document really emphasizes how Gaia's capabilities, the sheer volume of stars, the incredible precision, the ability to see faint objects are just revolutionizing our view.
Letting us map the dynamics of the bulge, the disk, the spiral arms, even that faint outer halo.
Yeah, it's giving us the data to trace how things are actually moving within all those components.
Yeah.
It's like um, finally being able to see the choreography of the galactic dance.
So if you had to boil it down, what's the single biggest achievement of Gaia that this source highlights for us?
I'd say it's that unprecedented ability to measure the distances and the motions, the kinematics for so many stars across so much of the galaxy with such high precision.
That's the game changer.
That's the absolute game changer. It's what lets us build that detailed picture of the Milky Way's structure and, piece together its evolution over billions of years.
And it wasn't just about measuring positions and movements, right? The source mentions the mission's design was key.
Oh, absolutely. A critical point in the source is the combination of astrometry, that's the precise position and motion measurement, with photometry.
Measuring the light.
Yeah, measuring the brightness and color of the stars repeatedly over time. Multicolor, multi-epoch photometry. Combining these was fundamental. It lets you not just track a star, but also figure out its physical properties, temperature, size, composition. Gives each star a detailed profile.
Okay, now there's also a mention of a table from Gilmore and Hugg back in 1995. What's that about?
Ah, right. That table's illustrative. It basically shows how astronomers plan to use specific types of stars as tracers for different parts of the galaxy.
Tracers, like markers.
Exactly. Certain types of stars are characteristic of certain populations,
Yeah.
like Cepheid variable stars trace young populations in the spiral arms, while certain old red stars trace the bulge or halo.
Okay.
So the table listed these tracer types, their typical brightness, where you'd expect to find them, how far away they might be, how much dust might obscure them.
And critically, whether Gaia could actually see them and measure them accurately.
Precisely. It showed the expected apparent brightness Gaia would see and the kind of precision it should achieve for their proper motions and distances. It was like a feasibility study, showing Gaia could target these key tracers across the galaxy.
So these tracers act like galactic lampposts, and Gaia needed to be powerful enough to see even the distant faint ones. Was that faintness limit important?
Hugely important. The source points out Gaia's faint limit down to magnitude 20 or 21 was specifically chosen for this. You need to see that faint to capture enough of these representative tracer stars way out in the halo or deep in the bulge or across the disk.
Otherwise, you'd only get a local view.
Right, a potentially biased view. You need that depth to get a fair sample of all the galaxy's main components.
And the conclusion in the source is pretty upbeat about Gaia managing this.
Very much so. It basically states that, based on the projected accuracy, Gaia can measure the proper motions, the side-to-side movement on the sky, for stars in all those key tracer populations.
With good precision.
Yeah, with significant, and often it's a superb precision. And measuring those tiny movements across the sky is fundamental to figuring out the galaxy's overall dynamics and history.
This has been incredibly insightful. It really paints a picture of Gaia as this revolutionary galactic cartographer. The scale is just immense.
It really is. We're talking about billions of stars mapped in unprecedented detail.
Okay, so here's something to leave our listeners with. Considering this absolute flood of super precise data Gaia is giving us, what completely unexpected things might we find? What unknown structures or hidden relationships within the Milky Way might this data reveal down the line?
That's the exciting part, isn't it? We've built this incredible tool, and now we get to see what secrets it uncovers. There could be remnants of ancient collisions we never knew about, streams of stars on weird orbits, maybe even refining our understanding of dark matter.
It really is like a vast, uncharted territory opening up. We've only just scratched the surface.